the lecture, and we'll see where we get to here for the rest of the time. So we're going to continue on and talk about naming here. So we started talking about at the end of the lecture there, again, some of the charges that are currently made by certain elements when they do get a charge, and a reminder that they really will only gain a charge when they are basically, in really the case of a metal and a non-metal. So when a metal and non-metal come together, that is essentially where they'll get the charge from. Before that, they really don't have charges. So as we see here on the periodic table I drew that we were looking at there towards the end, these are the guys that have sort of fixed charges, a number of them. So everybody in group 1 will always make a +1 charge. Everybody in group 2, a +2 charge. Group 3, a +3 charge. And then again, 5, 6, 7. And those are our non-metals above the staircase. We go -3, -2, -1. The transition metals and even the sort of metals in this area as well, below the staircase, things like lead, tin, antimony, and so forth. Bismuth is over in this area as well. These guys will have variable charges, which means they can make multiple charges depending on sort of who they sort of bond to and how many of something else they bond to. The only 3 sort of transition metals, as we talked about at the end there, that do have fixed charges is our zinc and our cadmium. So when they do form a charge, it's always going to be +2, and silver here will be +1. But pretty much everybody else in this sort of transition metal region and underneath the staircase will have those sort of variable type charges. And we'll talk about, what we need to do with those when we sort of name them. It's a little bit different. In general, a metal and a non-metal will form a cation, which is done by losing electrons. And how we name these ions, which are what these guys are, these are the formulas for the cations, for example. They do have the charges, as we talked about. We simply just use really the whole name of the element. So Na+ would be the sodium ion, as we talked about. Ca2+ would be the calcium ion, and so forth. It really is only the non-metals, which makes our anions over here as a result of gaining electrons, that we do a little bit different for, or a little different thing too. We do IDE at the end of the name. We do sort of remove the last part of the non-metal name and put the IDE there. So again, oxygen with a -2 charge, which would be the formula for the anion, would be oxide, IDE, dropping the last part there, a little bit more of it than of oxygen. Cl- again would be chlorine, again dropping the last part, IDE. And hydrogen as well, as I mentioned, is really the only one that could kind of go both ways, become positive or negative, depending on the situation. And we'll sort of talk about those. So knowing these charges, again, knowing those basic sort of ways we name it, really does help us name ionic compounds. And really, ionic compounds can be broken up really into 2 sort of types, type 1 and type 2. And really, the ionic compound is a metal and a non-metal. And whenever you have really this combination, the really most important one out of both of those things is always the metal. So the metal is always the most important one to look at. It really determines whether or not it is a type 1 or type 2 compound. So what is the difference between those? A type 1 compound is basically where the metal comes from group 1, 2, 3, or it's zinc, cadmium, or silver. And really what all these have in common is that the positive guy has a fixed charge. So it has a fixed positive charge. And that's different than a type 2 compound. A type 2 compound, again, it's the metal that's most important. And that metal will be a transition metal, or just to the right of it. And what these guys have in common are they do have that variable charge. So the first really main thing you want to think about when you are naming something that's an ionic compound, that's a metal and a non-metal, always want to look at the metal first, and that really determines how you go about naming this particular compound. Now, a couple of other important things when we write formulas for an ionic compound, it is always the cation first, which is the positive guy, followed by the anion. And that goes with both the name and also the formula. So always the positive guy followed by the negative guy. And that is always how we basically name them and also write the formula for these guys. So for example, NaCl, Na is sodium and Cl is chloride. And it is, although the formula itself has no charge, it really is made up of two things with a charge. It's made up of a sodium ion and a chloride ion. And the other really important thing about ionic compounds when we write formulas is when we put the positive guy together with the negative guy, it does have to equal 0. So again, one positive, one negative. When we put it together, we just need one of each. So those two things are really important in terms of formulas for ionic compounds. Always the positive guy first, then the negative guy. And when we write a formula for an ionic compound, which is composed of a cation and anion, the overall guy should have an overall charge of 0. So there's no actual charges written in the formula for the compound, but it is basically made up of two things that do have charges. So those are two important things to keep in mind as we kind of go through this. So let's take a look then at some of these here. And again, this is earlier, kind of what we talked about earlier. This is just positive cations. And you can see simply we just use the name of them. And again, you could write ion after each of these. And again, you can see that the charge is written into the actual formula for the ion. Otherwise, it would not be an ion. So you just put the charge in. These are all negative guys, anions in this case. And you can see they all end in that IDE. So fluoride, chloride, bromide, iodide. So let's talk about type 1 compounds and how you go about naming them. Type 1 is pretty straightforward. Type 1 ionic compounds, again, is going to be the metal and the non-metal. And it is the metal that is that guy with a fixed charge, which means it's group 1, 2, 3, zinc, cadmium, or silver. As soon as you identify it as a type 1 compound, that is pretty much all you need to do. You then basically take the metal and you use the whole name. And you take the non-metal, you drop the last part, and you replace it with that IDE. And that is pretty much all you need to do when you can identify it as a type 1. Like if we did look at this, sodium, which is a metal, Cl, which is chlorine, which is a non-metal. When I look at the periodic table, I see that is group 1, which means it has a fixed charge, which means that is all I need to do. I don't really have to worry about anything, charges or anything like that. I know that the whole name of Na is sodium. Whole name of Cl is chlorine, which then becomes chloride. So that would be sodium chloride. If I take something like KBr, I look at K, that is a metal, and that is group 1 as well, which means it has a fixed charge. So that is as far as I need to worry about it. I use the whole name of the metal, which is potassium. The non-metal gets the IDE at the end, and it becomes bromide. Any questions on that there? So type 1 ionic compound, it's a metal and a non-metal. The metal is the most important guy. It will either be from group 1, group 2, group 3. It will be silver, cadmium, or zinc. And that means that all you have to do is use the whole name plus the IDE on the non-metal name. Now, again, it's important as we see here, as I mentioned, when we look at something like Ki, again, K is group 1, so we use the whole name potassium. Iodine becomes iodide. And again, although it is, when we look at the overall formula of Ki, or even like our NaCl, or even like our KBr we were looking at, although the formulas for the ionic compound, which contains both the cation and anion, positive and negative guy, they do not have charges, but they do represent basically two things that have a charge. The cation here would be potassium with a +1 charge. The anion would be I with a -1 charge. Again, if you take +1 and -1, that equals 0, which is why the formula looks like that. Absolutely no charges written in there. Same thing with our sodium chloride. Again, the cation here would be sodium with a +1 charge. The anion would be Cl minus, again, +1 -1. Absolutely no charge needed. And that's why we just have one of each of those. Here, potassium bromide, again, cation would be K plus, anion would be Br minus, +1 -1. Again, absolutely no need for any type of charge. Take a second here and tell me what this guy would be called. Actually, let me change it. Let's do this guy. So what would the name of this guy be? Let's take a second. Okay, so if we look at this again, Ca is a metal, Cl is a non-metal, so that automatically tells us it's an ionic compound. The Ca is from group 2, which means it does have a fixed charge, which means that's pretty much all we need. And this would be calcium, whole name of the metal, IDE for the non-metal, and this would be calcium chloride. Now, an important thing to note is this is calcium chloride. This is not calcium dichloride, which a lot of people like to call it, which is incorrect. The 2 here has no effect on the actual name. You could have like a 40 of them and it will have no effect on the name. The 2 has no effect on the name when you're doing this type of naming. Why do we have the 2 there? Well, if we look at calcium, which is group 2, the cation in this case is calcium with a +2. The anion is actually group 7, which is chlorine or chloride, which is Cl minus. So if we were to put these guys together exactly like this, we have +2 and only -1, and that's not going to balance out the charge to 0. We actually need not 1 Cl minus, but we need 2 of them. +2 and -1, and -1 is -2, gives us our CaCl2 as the proper formula. Again, no charge because the overall charge balanced out to 0. But again, this 2 has no effect, and you should never use a prefix in this type of naming. So this would be called just calcium chloride. Any questions on that there? All right. Oops. So let's take a look here. Take a look at a few of these here. This is potassium, again, group 1. So we use the whole name. And again, chlorine becomes chloride. This is our calcium and Br. Again, calcium group 2, which has a fixed charge. So whole name of calcium. Again, the anion, even though there are 2 of them here, would just be called bromide. And again, the reason for that is if we look at the cation up here, this is K plus, and the anion is Cl minus. Again, one of each of those gives us our formula. When we come here, our cation is calcium with a +2. Our anion is Br minus. So in this case, to balance out the charge, we do need one more of the Br minuses, which again is why there is a 2 in the formula here to give us our correct formula of CaBr2. But again, has no effect on the actual name. BaH2, Ba is barium, which is a fixed charge metal. So we use the whole name of the metal. And in this particular case, this is hydrogen that's actually negatively charged. The cation here is our positive barium with a +2. The anion is a -1 charged hydrogen. And in this case, same idea here. We want to balance it out to 0, which means we need 2 of the negatives here to balance out the 2 positives. And that gives us our BaH2 in this particular case. Now, hydrogen is kind of an interesting thing. If we have something like HBr, for example, here the hydrogen comes in front. Here the hydrogen comes second after a metal. In this particular case, the cation would actually be H plus. It would be the positive version of hydrogen. And that's because the anion in this case would be Br minus. And in this case, we kind of treat hydrogen usually as like a type 1 compound, which means we would just call this hydrogen bromide. Any question on those there? All right, so why don't you try some here? Let's do, give the name of this guy, give the name of this guy, give the name, go like that there. Give the name of that guy. And while we're at it, let's also give the formula for, let us do lithium. Let's do lithium phosphide. Let's do barium chloride. And let us do, let's see what we got going here. Let's do that. Let's do potassium oxide. All right, take a couple minutes. Let's do correct names on these guys and give it a go for our formulas. Again, the goal with the formulas is to get an overall charge of 0. And you actually want to do it in the simplest way that will get you to 0. So take a couple minutes and we'll talk about these here. Okay, let's take a look, see how we're doing. So again, we want to approach this really first off by identifying what you're dealing with. So Mg is a metal, Cl is a non-metal. So that automatically should scream to you that you're dealing with an ionic compound. Whenever you're dealing with this situation of a metal and non-metal, it is the metal that's most important. And when we look at the periodic table, we see that magnesium is group number 2, which means it has a fixed charge. So that should then scream to you that this is a type 1 compound. And that's basically all you need to worry about at this point. We then will use the whole name of the metal, which would be magnesium. The non-metal then would get the IDE at the end of it. And remember that the 2 has no effect on the name. And again, the 2 is there because the cation in this case is magnesium with a +2 charge. The anion is Cl with a -1 charge. And again, the reason we have the 2 there is we need 2 of those negative charges to balance out the positive charge we got going on with the magnesium. Any questions on that one? All right, same thing here. We see sodium, which is a metal, oxygen, which is a non-metal. So again, that tells us ionic. The sodium is group 1, which tells us it's fixed and is a type 1 guy. That then means we don't have to worry about anything other than writing the whole name of the metal. So this would be sodium. Oxygen becomes oxide. And much like the 2 on the end on the first one, this 2 has absolutely no effect on the name either. Again, we would not use a prefix or anything weird like that here. It would just be sodium oxide. The reason, again, we have the 2 there is the cation in this case is a sodium that has a +1 charge. The anion is oxygen, which is group 6, has a -2. And that is why we need 2 of the sodium ions to balance out the -2 charge that we see on the oxygen. Any questions on that one there? Lastly, here we have Al, which is aluminum and a metal. We have S, which is sulfur, it's a non-metal. Again, the metal, non-metal tells us it's ionic. The aluminum, which is group 3, tells me it's fixed in a type 1. That means even though there's a bunch of numbers on the bottom there, don't really care. This will then become aluminum, whole name of the metal. I can scribble it out there. Sulfur, we drop the last part and become sulfide at the end of it. Again, we have the numbers because we need to balance out the charge. And again, in this case, the cation is an aluminum with a +3 charge. The anion is a sulfur with a -2 charge. Common number is 6. So I need 2 aluminums, gives me +6, which is why there's a 2. And I need 3 of these sulfurs with a -2 charge, which gives me -6. So that's why there's a 3 here. But again, in this type of naming, the 2 and the 3 has really no effect on the actual name. Any questions on how we got to those names? Okay, so obviously we do need to go the other way, which is, if we're given a name, what is the correct formula? So this is what we were talking about earlier and what we saw above here as well. The key thing is when we put the positive guy together with the negative guy, we want to end up with an overall charge of 0. And we want to do it in the simplest way that will get us to 0. So where should you start if you have the name? Well, if you could see the name like lithium phosphide, lithium is a metal. Phosphide is phosphorus, which is a non-metal. So again, that tells you it's ionic. And what you want to do is just get the basic ions that make that up. So lithium, which is group number 1 on the periodic table, means that the cation we are dealing with is Li plus because it's group 1. The anion, which is phosphorus, group number 5 on the periodic table, will actually have a -3 charge. Now, the goal here is to put these together in a way, the simplest way to get to 0. And when we look at it, we really need not 1 lithium, not 2 lithiums, but we actually need 3 lithiums with a +1 charge to balance out that -3 charge we got going on over there. Basically, we just count it 1, 2, 3. That means I have 3 lithiums. Again, the number goes to the guy to the left, and 1 phosphorus, and it would be Li3P would be the proper formula for lithium phosphide. Any questions on that there? Now, sometimes people are taught to do the kind of crossover move. And to be honest with you, it works 90-ish% of the time. It doesn't work 100% of the time. What I mean by that is if you took something like the lithium and you took something like the phosphorus, if you bring that number down and that number over there, you get Li3P1. And again, it works in 90 some odd percent of the time, but definitely is not 100% working all the time, will not be perfect one all the time. So sometimes it's best to think about it just like what I'm doing here, even simply draw the things and just count up the charges to make sure that it does balance to 0. Looking at the next one, which is barium chloride. Again, barium is group 2 and it's a metal, and chloride is a non-metal. So the cation here is going to be the barium that has a +2 charge. The anion will be group 7, which is a -1 charge. Again, when we put this together, we have a +2, only a -1. So we do need one more chloride there to balance it out. And that gives us a formula of 1 barium and 2 chlorides. Any questions on that one there? All right, lastly here, maybe I'll make a little room here so I got somewhere to scribble. We'll go over here. Yeah. Last one's potassium, which is a metal, oxide, which is oxygen, which is a non-metal. So potassium is group 1. So the cation here would be a K+. Oxygen, which is group 6, would be our anion, which is a -2. Now, when we put this together, -2 + 1, we need one more potassium to balance out the charge, and that gives us K2O in this case. Again, none of the formulas have charges. And again, you should never have a charge when you are writing a formula for an ionic compound. Any questions on type 1 compounds and how to name them? Obviously, you need to be able to, if you're given the formula, give them the proper name. And if you're given the name, give the proper formula. And obviously know what the cation and anion is. Any questions on any of those? By the way, in terms of the anion for something like what we have somewhere, where am I here? For something like this, again, it is Cl-. It is not Cl2-. That is not correct. So the 2 here again means that you have 2 individual -1s, and make sure you use the correct formula there. All right, then that brings us to type 2 compounds, and type 2 compounds are a little bit different. Type 2 compounds are ionic compounds as well. They still have a metal and a non-metal, and it is still the metal that's really important here. The metal, though, is going to be a transition metal, or just to the right underneath the staircase, where we have things like lead, tin, in that general area. And what these guys really, again, all share in common, as I mentioned earlier, is they have a variable charge, which means in certain cases they may be +1, other cases maybe +2, maybe +3, +4, and so forth. So when we name these guys, the goal here is really to tell people, what charge we're dealing with. So if we take something like this, FeCl2, we really do just want to approach it the same way as we've been doing with the other ones. Fe is iron. It's a transition metal, dead center almost on the periodic table there. Cl is a non-metal, which is chlorine. So again, metal, non-metal tells us it's ionic. The location of this iron, which is, again, if you look in the periodic table, like right there in the transition metal region, tells us it's a type 2, which basically tells us it has a variable charge. So how do we go about doing this? Well, the first thing that we need to do is to kind of figure out what is the charge on that metal. So we may not know what the charge is, but the good news is you will always know the charge on what it's bound to. So that is Cl, which is group 7, which means it is Cl-. And again, there's not just one of them, but there are 2 of them, which means overall negative charge is -2. So in order to balance out that formula to 0, The iron in this case will have a +2 charge to balance it out. So the good news is when you're dealing with these type 2 compounds, although you may not right off the bat know what the charge is on the metal, you definitely will know what the charge is on what it is bound to. And you can basically work your way backwards and be able to figure out the charge. So now that we figured out the charge, what do we do with it? Well, type 2 is pretty much named the exact same way as type 1, which means that we use the whole name of the metal. We use the non-metal like we did before with the IDE. The additional thing that we do is we put a Roman numeral in between. And what does the Roman numeral mean? The Roman numeral is the positive charge on the metal. So when we come to a thing like this, whole name of the metal, which would be iron, Roman numeral 2, not for how many metals you have, but for the actual positive charge that we see on one of the metals. And just like before, even though there are 2 chlorides, has no effect on the name, and we would call this iron 2 chloride in this particular case. Question on that name there. So why do we need to call it iron 2 chloride? Well, if we took something that was very close to that, like FeCl3, in this case, we would look at the iron and not know what the charge is. We would have 3 of the Cl minuses, which gives us a grand total of -3. In this particular case, the iron would have a +3 charge versus a +2 charge. And the name of this guy would be iron Roman numeral 3. Again, chloride, regardless of how many there are. And again, the 3 is the positive charge that we have on the metal. So really, when we're dealing with type 2, because they can have a variable type of charge, we need to tell the person, hey, in this case, we're dealing with the iron with a +2 charge. In the other case, we're dealing with the iron with a +3 charge. Any questions on that there? Now, if we look at this guy here, which is PbO2, again, lead is not necessarily a transition metal, but if you look at lead, it's like down here below the staircase. But those guys over here, like I said, where lead is, there's antimony, there's tin. They are also named as type 2 compounds. So what that means is we really don't know what the charge is on the lead, but we do know that oxygen is group 6 and it has a -2 charge. And there's not just one oxygen present, but there are 2 of them, which gives us a grand total of -4. Which means the charge actually on this lead is +4. And that means that this name would be lead Roman numeral 4 because of the charge. And again, even though we have 2 of those oxides, we would just call it oxide in this case. Question on that one. Now, this is also a really good example of earlier I was talking about sometimes people are taught, kind of do the crossover move with the charges. And this is a very good example that it will not work correctly. So if you went crossed over that way and that way, you might find yourself thinking it's lead 2 and the oxygen has a -1 charge, which are both incorrect in this case. So again, if you want to use the crossover thing, you can, but remember that it doesn't work 100% of the time. And there's a lot of cases where it will not work correctly. But, if you're good with 90% of the time, then you could kind of do the crossover move. Now, there is an older way of naming, which we're really not going to sort of use in this class, but sometimes it does come about, and that is instead of using Roman numerals, we use sort of the old way of naming things. So instead of iron, we call it ferric or ferrous, and typically the one with the IC has the larger positive charge, and the one with the OUS has the smaller positive charge. And they also, obviously, as you can see, use the kind of historical name rather than iron, from ferrum, but we won't use that in this class. Occasionally something like ferric or cupric for copper come up, but again, we should use Roman numerals in this class, and most of the time people will use Roman numerals. Here again are some examples of some of these variable charges type of guys. One thing we should note over here is Mercury is kind of a weird one. Oddly, the Mercury that acts like this versus the Mercury that looks like this. This guy with all of the twos are oddly Mercury 1, as opposed to the guy that has just 1 2, he is Mercury 2. The reason for that is really 2 Mercury 1s together, sometimes referred to as a dimer, and just how they naturally come together. That's why there's a 2 on the bottom, and it's +2 overall, even though it's made up of 2 individual 1 guys. So oddly, Mercury's the only weird one like that. The guy with all the 2s is Mercury 1. The one with just the 1 2 on top is Mercury 2. Sometimes people go, well, how do I know? Well, usually that 2 that's on the bottom kind of stays around as you write it in a formula. Like this would be Mercury 1 oxide as opposed to Mercury 2 oxide. So that 2 that's down here kind of hangs around in the actual compounds formula. And that's how you can usually decide that it is kind of Mercury 1 versus Mercury 2. Any questions on that there? All right. So the rules are, as I mentioned, pretty much identical to our type 1 naming. Whole name of the metal, IDE for the non-metal. Again, doesn't matter how many you have of any of those, that's the format. The only additional thing that we do is we use that Roman numeral to indicate the charge on the metal. Again, the individual positive charge on the metal, not how many we actually have, which is a common error that people make. So let's take a look at these guys here and see how we go through it. Here we see CO, which is cobalt, which is a metal. We see Cl, which is chlorine, which is a non-metal. Again, cobalt, if we look on the periodic table, will put us in the transition metal region. That again should tell us is type 2. It has a variable charge. So basically we could just work it out like we did before. There's 1 cobalt, chloride is -1, and there are 3 of them. Again, to balance out this -3, that has to be +3, and putting that together would then get us cobalt Roman numeral 3, again for the charge. And even though we have 3 of those chlorides, it is just simply called chloride. Again, no prefix or anything like that. Any questions on that one there? Looking at this one, we see Cu, which is copper, which is a metal. We see I, which is iodine, which is a non-metal. Again, tells us it's ionic. Always the metal is the important part. Again, copper there in the transition metal region tells us it's type 2, can have a variable charge. We rolled just like we just did. 1 copper, not sure what the charge is, but iodine is group 7, which means it has a -1 charge. That means in order to balance it out, that must be a +1 charge. And then this would be copper, whole name of the metal, Roman numeral 1 because of the charge. Iodine becomes iodide here in this particular case. Any questions on that one? And Lastly, here we have SN, Br4, again, SN, which is 10, which is actually just to the right of the transition metal region. Again, remember those guys just to the right are also basically type 2 metals. Here again, Br being our non-metal. So following our same approach, I have 110, which I'm not sure what the charge is, but I do know that Br is group 7, which means it's -1, and there are 4 of them. That gives me a grand total of -4. That means in this particular case, the 10 should carry a +4 charge to balance it out. That then would give us 10 Roman numeral 4. And then again, even though there's 4 of them here, we get the IDE treatment, and we would have 10 Roman numeral 4 bromide. Any questions on that particular one there? We know it's type 2, and whenever you're dealing with an ionic compound, regardless if it's type 1 or type 2, it is always the metal part that's most important. So when we look at all of the metals that are here, pretty much in this example, the cobalt is in the transition metal region, the copper is in the transition metal region, the tin is just to the right of the transition metals, and pretty much everybody in the transition metal region and kind of to the right of it basically are what are considered type 2 metals, which basically means that they can have a variable charge, which is why we do have to include the Roman numerals in this case. And that's again how we know it. There are only 3 exceptions in the transition metal region that do not have a variable charge. So within that transition metal region, as I showed earlier, zinc, cadmium, and silver, they are transition metals, but they have fixed charges. So these guys are actually type 1 metals, along with everybody else in group 1, 2, and 3, because they do have those fixed charges. Question on that?